n minus n greater or equal to 0, h equal to b n prime n prime minus n prime greater or equal to 0. If g is isomorphic to h, then n minus n is equal to n prime minus n prime. So how do we actually go about this? Let me just talk about this a little bit. So there's if two groups are isomorphic, if g is isomorphic to h, that isomorphism induces isomorphisms on its corresponding quotients. So if g is isomorphic to h, then g mod g1 is isomorphic to h mod h1. g1 mod g2 is isomorphic to h1 mod h2. g mod g2 is isomorphic to h mod h2, etc. So because of this isomorphism between g and h, it induces isomorphisms on their quotients, on the corresponding quotients. So it turns out that when we look at g mod g1, we take g and we just abelianize it. We add the relation AB equal to BA to the original relator. And what do we get? We do a series again of Tissot transformations. And it turns out that g mod g1 is actually a direct product of C infinity cross Cn minus m.
Can you write it on the paper?
Okay, so it turns out that when we look at this here, so I want to take a look at this. This element here, in other words, we have a presentation of the form
write out the original presentation that you got from...
Well, we start off from g mod g1, b, and then so that means Tissot transformations. And it turned out that the last step, of course, we just convert it into, of course, a direct product because we're going to have that. So it turns out that just by this relation here, the presentation, the element that gives rise to torsion is the B element. So at some point I would like to kill that torsion subgroup. So I'd like to mod out by the torsion subgroup. So this also occurs for H, that H mod H1 is isomorphic to C infinity cross C n prime minus n prime.
What is H? Oh, this
H would be the corresponding...
The
yeah.
The other
So
one.
then they show the orders.
Yes, exactly. Two finally generated abelian groups are isomorphic, then the corresponding torsion subgroups are isomorphic.
Interesting.
They have the same cardinality, hence it shows that n minus n is, well, so actually prove it without saying it.
Yeah.
Okay, so we have that relation and we're going to use that later on.
The trick really is to resist temptation to be efficient with the recognition of what the presentation does. Just manufacture it on the surface.
So again, this is lemma 2. If g is equal to bmn with n minus n greater or equal to 0, if S mod g1 is a torsion subgroup of g mod g1, so we're working in terms of the quotient, then these are all true. Okay, so there is some work involved here. We have to show that this set is a group, it's a normal subgroup, and it turns out that it's equal to the normal closure of B in G. And again, by the Magnus breakdown of one related group, this is actually the presentation of the normal closure of B in G. That's what I was alluding to before when we use B23. And it turns out that since S would be the torsion subgroup, because where the element GK lie in G1. So if we just take S and we mod it out by G, we kill the torsion. In other words, we just take the presentation and we just add B is equal to 1. We kill all the B's. And hence it's torsion free. That is G mod GS is isomorphic to the infinite cyclic group. So the idea of this we're going to use further on when it gets a little bit more complicated. This is just looking at just G mod G1. So I want to look at the cases when n minus n is equal to 0, and then n minus n is greater than 0. Now it turns out that when n is equal to, so I'm looking at this part now. Why can I say that the center of BMM is equal to the group generated by B to the M? Again, that takes some work. So let me just tell you what you do. Well, when n minus n is equal to 0, that means n is equal to m. So you go back here. When n is equal to m, this is like C0. But n is equal to m, this is just the input. So C0 is the same as C infinity. Okay? So we get C infinity cross C infinity. So it means that if we look at the G mod G1, we really cannot identify, we cannot do anything, no information, we cannot get any information from looking at just G mod G1 when n is equal to m. So we have to do something further. Okay? So I look at the center. So notice when n is equal to m, because of a simple Tietze transformation, G would have this form. Agreed?
Yes.
So this is m. Okay?
Good.
So it means that B to the m commutes with A, B to the m commutes with B, hence B to the m commutes with the generators, hence B to the m is the entire center of G.
Sure.
Yep.
Okay?
Can do anything.
Okay.
Good. So which means that if we take G modular the subgroup generated by B to the m, and we do a Tietze transformation again, we could present that group, and it turns out to be the direct, the free product of, say, C infinity, I call Z, is the same as C infinity, star Cm. Okay? So, you know, again, we just take this presentation, we add B to the m, and again we do a series of Tietze transformation, and it turns out that the last one, we could represent it as a free product of C infinity star Cm. Okay? Again, we do this for H correspondingly. And again, we get a relation now, M must equal to N prime. So the same occurs here. Again, they're isomorphic. So Zm is isomorphic to Zm prime, hence M is equal to M prime. Okay? So now we actually solve at least that first part when n minus n is equal to 0. Because if n is equal to m, this forces the relation that we have up. This forces this relation. N is equal to m. N prime is equal to m prime. Hence, we just got m is equal to m prime. Hence, n is equal to n prime.
This is just a side comment. You know, what you just said now allows you to compute a profile function for those groups right away.
Well, we can talk
You
about
have the
that.
great geometry.
Yeah, we can talk about it later.
Yeah, I
So-
just wanted to let you know that that's I already figure out from what you said.
Okay, so this follows. So now we want to take a look at when n minus n is greater than 0. Well, if you do some work, when we have n minus n is equal to 1, for example, things work out pretty quickly. We can still look at G mod G1 and its infinite cyclic. So the problem we want to be able to, when it's greater, we have torsion here, and I want to be able to kill the torsion. So if I take this and I monitor it by, I want to be able to have that quotient to be torsion free. Okay? So again, from now on also we can do the same for H. The same procedure applies for H. We can present the normal closure of Y in H this way, and H mod T is isomorphic to Z. Okay? Yes?
Mm-hmm.
So So now we're in position to formulate the following lemma, whose proof relied on ideas similar to those of lemma 1. That if G is equal to Bmn, with n minus n greater or equal to 0, or greater than 0, sorry, and H, m prime, n prime minus n prime greater than 0, and phi is an isomorphism between G and H, then if we put P mod S1 and Q mod T1 to be the torsion subgroup of S mod S1 and T mod T1, respectively, if G is isomorphic to H, then G mod P is isomorphic to H mod Q under the isomorphism phi star, and S mod P is isomorphic to T mod Q under the isomorphism phi sharp, okay, where these are the induced isomorphisms. Now we can analyze certain actions inherent in the quotients of G. And from lemma 1 we see, remember G mod S was infinite cyclic. So it turns out that we could present G in the form of S by A, where A is the infinite cyclic group on A. So we can express G as a semi-direct product. Now it turns out that if we look at S mod S1, this is the same as S, the Bi sub I is generated by the B sub i's, and the relation B sub I to the m equal to B sub I minus 1 to the n. So we just idealize it. We've just add the commutator Bi, comma Bj equal to 1. But we are not sure if this has torsion, so we want to kill the torsion by taking S mod S1 modular this P mod S1. Okay? So which means that S mod P would be torsion-free abelian. Okay? And the same would be, we can do the other in the other group, T mod Q. Yes? So because it's a semi-direct product, remember we have G is a semi-direct product of S by A. This also induces, the action induces similar action on the corresponding quotient. So if you notice again, if we look at G mod S, modular S mod S1, we still get it infinite cyclic. The A S1, which is the that particular coset, is infinite cyclic again. And we can keep on doing that. We take G mod S1 modular P mod S1 is equal to S mod S1 modular P mod S1 by this particular infinite cyclic group. Now because S is a subgroup of P, then everything gets kind of sucked in, so to speak. And we end up with G mod P by the third isomorphism theorem is isomorphic to S mod P by AP. It turns out that because of the cumbersome, I let L to be equal to G mod P and let B sharp to be equal to S mod P. Now recall what I had before. What was B sharp or T sharp? T sharp map S mod P into T mod Q. So that's a nice notation. I call it B sharp. T sharp would map B sharp to Y sharp. Okay, so
Very sharp.
Sounds pretty sharp.
no, but I mean it's kind of to keep track because things get very confusing here. Yeah, so the notation kind of suits the particular cases I have.
Can you explain the third isomorphism thing?
Hey, you should know that, come on.
So, you see what I'm saying? Remember P star map G mod P into H mod Q. And I said S mod P, well, it's on the other slide. So once you keep on doing that, once we, a typical element of L, because L is a semi-direct product, has this particular form. Remember what a semi-direct product was? That S is a normal subgroup of G.
I have to say I'm losing track of all of these different
I know. It's a lot to
Can you just remind me?
Maybe you're right, I don't know.
Yeah, just on the side, maybe just, I know what G is and I know what H is. It's that far.
So-
I'm
yeah,
okay.
but remember,
S and T were the torsion.
Okay.